I'm very excited to be invited to talk to you here and to share some thoughts and experiences with you. Thank you to Alexander Fleiss and the MIT Sloan Quant Finance Conference for inviting me. When Alexander invited me to speak here, he suggested that I might talk a little bit about my adventures in building Alexa when I worked just down the street here at Amazon. 12 years ago, before that, I was the VP of research for Yap, a small speech recognition company. When it came time to sell the company, we were courted by Google and Amazon and others. And in the end, we agreed to the purchase by Amazon. And we wondered, what was this e-commerce company going to do with a speech company? But they wouldn't tell us anything about their plans. So in late 2011, 12 of us from the acquisition found ourselves in a locked conference room in Amazon's offices in Seattle, eager to hear what they had in mind for us. The sale of the company had happened a week earlier, and we still didn't know what we were supposed to be doing. That was where Greg Hart, Al Lindsay, and others laid out Amazon's vision for a small voice-only virtual assistant, codenamed Doppler, which is now called Alexa. It would sit on your kitchen counter or your nightstand or in your garage or wherever, and you would interact with it by natural speech. And their initial vision was remarkably similar to the Echo Dot that you might buy today. That sounds like a comfortable, familiar scenario to a lot of us now, but a decade ago, it was total science fiction. In particular, there was no technology at the time for computers to recognize speech from more than a few feet away from the microphone, which is often called far-field speech recognition. So I was in the uncomfortable position to let Amazon know that their vision was unrealistic. They had just spent tens of millions of dollars for something that couldn't be done. Amazon, however, was just not fazed. They said that they were comfortable taking the risks and pushing the boundaries. They told me to hire as many of the brightest minds that I could for the project, and they gave me unlimited computing resources for my team. By the time Alexa launched 3 years later, I had built the largest speech science team ever assembled at that time, with more than 80 PhD level scientists working in 5 labs around the world in Seattle, Silicon Valley, Cambridge, Massachusetts, Cambridge, England, and Aachen, Germany. It was exciting. It was heady times, a lot of fun, working with great, smart people on a very challenging project. In the end, we did succeed. It took us 3 years, and there were, I would say, 3 key factors to our being able to put the technology together for the Alexa launch. The first is we hired talented, skilled people. We scoured the world for the best and the brightest. We hired every new top PhD that we could find. We had super high standards, so even people that I thought were amazing got rejected because we couldn't get the entire hiring committee to agree that they were going to raise the bar. Second point was data collection. We hired a whole team of specialists in data collection. A lot could be said about this, but I'll save that for another time. Let's just say that it was a challenge and an adventure to record thousands of people speaking thousands of hours across the USA with different accents, saying different things, a variety of indoor settings, all without tipping our hands about what we were working on, the big secret of what we were trying to build, because it was a big secret. And the third key to our success was a very technical one: deep neural networks. This might have been the biggest success factor for Alexa. It's a bit of an arcane topic, and I don't usually get to talk that much about it because it's relatively technical, but hey, this is a quant conference, so let me go into a little bit of detail here. I apologize to those of you for whom this is already well understood, or to those of you whose eyes glaze over when things get technical. I'll try to keep this accessible, but it's also an important topic right now to recall because it's very closely tied in with what's going on now with things like ChatGPT or DALL-E 2 or other large language models, which are getting a lot of attention. Traditionally, we have recognized speech in roughly 3 steps. There's the acoustic model, the lexicon, the language model. The acoustic model represents the connection between the acoustic signal and the individual phonemes of the language. English has roughly 45 phonemes. We have 26 letters, 45 phonemes, sounds of the language. And so the acoustic model would help us figure out where in the speech, if you look at a point in time, we could say, oh, they're saying a sh or a oo or a p or whatever, but just identifying what phoneme is being said at that time. The lexicon represents the connection between individual phonemes and those words that we have. So we have like essentially a pronouncing dictionary so that we know how the phonemes connect the words. And then the language model knows how words fit together into phrases and sentences. The ASR engine, ASR is the term we use. It means automatic speech recognition, as opposed to human speech recognition, which you and I do when we recognize what people are saying. Automatic speech recognition, we just say ASR. So the ASR engine uses these three models to decipher the phrases and sentences that were said in a particular acoustic recording. The trickiest part of all of this is probably that first one, the acoustic model. How in the world do you look at a point in the acoustic signal and know what phoneme is being said? Up until about 2010, the dominant approach for recognizing the phonemes in a speech signal involved doing a spectral analysis of a frame of audio, and then we have a model that would describe where we would describe that frame with, I don't know, a couple of dozen numbers, and then we would have those numbers would have some representation in like 24-dimensional space of where the sh sounds clustered or where the oo sounds clustered and so forth. And we had a way of describing those clusters using Gaussian mixture models, or GMMs. And that worked reasonably well. We got pretty good accuracy with that approach. But probably the main advancement that allowed us to recognize robust far-field speech for Alexa was the application of deep neural networks to acoustic modeling. So instead of that approach of Gaussian mixture models, here instead, we calculate an array of numbers from the audio in a given frame, maybe a couple hundred numbers describing that slice in time, and we pass that through several layers of a neural network. And the final layer, if we've done it right, will contain, it'll be a 45 long vector that will contain a score for each phoneme, each of our 45 phonemes. And if we've done it right phoneme will have a high score, and we'll be able to say, there's a sh sound going on there, whatever. It probably makes sense for us to zoom in a little bit, however, and look at what's going on between each pair of layers. So computing one layer from the next, we do basically two things. First, we multiply by a matrix. So if the layer above has 300 numbers and the layer below has 200 numbers, then we have a 300 by 200 matrix. We just multiply the top array by this 300 by 200 matrix. We now have the new 200 long array for the next layer down. But the next thing we do is to prune away the small number. So we apply what we call an activation function that says we basically boost numbers above a certain threshold and prune numbers below a certain threshold. All the details, there are a handful of different approaches that people like to use for this. And I won't focus on that here. The real complexity of the model is in these matrices that represent the transformation from one layer to the next. Although I don't want to ignore that activation function. Without that activation function, this is just a sequence of matrix multiplications. You can just multiply them out, and it's essentially one matrix multiplication, and it's not very interesting. It's that activation function that makes this nonlinear and makes it kind of interesting. And by the way, it should be said that inspiration for that is that's also how our brains work. The neurons in our brains do essentially what I just described. They take inputs from other neurons and they apply an activation function to decide if they are going to fire or not. So when it comes down to it, the entire acoustic model is represented by four kind of big matrices plus the details of our activation function. But remember, this is just an improvement in one step of a larger process. We still have to do the acoustic analysis to get those numbers to feed into the AM. We still have to, AM, acoustic model, right? We still have to do the search that incorporates the lexicon and the language model. But this one improvement in the DNN AMs allows us to recognize speech with much more robust acoustics. So different rooms, different acoustics, different speakers, different accents, different noise conditions, fans, appliances, televisions. When I first started in speech 27 years ago, has it really been that long? We had different models for men and women. If you remember using products like Dragon Dictate or Dragon Naturally Speaking, back in the 90s or so, you had to train the model to your voice. Well, we've moved way beyond that, right? Now we've got this very robust DNN-based acoustic model that represents different speakers, different environments, different conditions, and in particular, it allows us to represent far-field speech, which is very cool. It's important to note that we can't point to where the model is capturing the different things. I can't point to a place in those matrices. Remember, those 4 blocks, those represent my 4 matrices that govern that deep neural network model there. I can't point to where, oh, right over here, that's where we're handling the noise of a dishwasher. Or over here, that's where we're handling a Hispanic accent. Or over here, that's where we're handling people who pronounce words in a certain slightly different way or whatever. Or the reverberations of a large window. The training algorithms just take a whole bunch of data, and we ask those algorithms to come up with matrices that are going to give us the answers we're looking for, the correct scores for those phonemes. This is one of the things that's frustrating about this new deep learning approach. We don't always know what the machine is doing. We just know that it works. It's just a bunch of matrices. We don't really know what the numbers are doing in that hidden layer. We know the top layer. We understand the numbers we're putting in, and we think we understand the bottom layer of what is it giving out. It's giving us those scores for phonemes. But what's going on in between, it's a mystery, and it's exciting and it's frustrating all at the same time. All right, so 3 years at Amazon we spent building Alexa, and we finally released it to much acclaim, and it's still one of the best things I've ever done in my career. But there is more to speech tech than virtual assistants. When I was at Amazon, I was regularly approached by people within Amazon wanting our speech tech for other Amazon projects, but we had to focus on Alexa. We had to turn all those people down. While Alexa was a very interesting and challenging problem, there were a lot of other interesting speech problems we just couldn't take on. Take, for example, the problem that a financial analyst has of dealing with quarterly earnings calls in real time, right? So here I put some bullets on this slide. You'd ideally like in real time to get a transcript, annotation on who is speaking when, because you'd want to know when the CEO turns the floor over to the CTO or whatever. You'd like to know an analysis of the prosody. When are they pausing? How fast are they speaking? How loud are they speaking? To the extent that that might mean something. Speaking of what it might mean, what if we did a higher level analysis to figure out underlying factors like a level of anxiety or a level of engagement or so on? And never mind all of that, we also would like just an analysis of what's being said, right? When they say those words, what does that mean? Oh, that means that they outperformed or whatever. Or maybe you can think of other things you'd like to analyze when you're having and processing an earnings call. And it would be nice to have that happen in real time for the analyst, and perhaps to even automate some processes that might come on top of that. But Amazon wasn't going to chase that. Wasn't going to pursue that, right? And so I just use this as a specific example, but there were many things that I wasn't able to be working on at Amazon, and it was a little frustrating to me. We had solved to some extent the Alexa problem, and I wanted to move on and do other things. So after 3 years at Amazon in 2014, I founded a new company Cobalt speech and language. And we have developed at Cobalt, we have developed speech recognition, our own speech recognition, text to speech, speech analytics, like analyzing speech to detect emotion or age or gender, things like that. Speaker identification, who's talking, from maybe a bank of known speakers. Conversational interfaces, so you can talk to an appliance or an application or something like that, and so on. So we've got a large array of speech technology that we then bring to bear, that we license to other companies, and we also consult with people on the best ways of using it and applying it to their particular domains and so forth. Cobalt has also spun off a couple of interesting companies. Canary Speech, which does analytics for healthcare, very exciting company, where we can use speech to determine the likelihood that you have anxiety or depression or Alzheimer's or Parkinson's or other diseases. And we've also spun off a company for doing legal documentation, for transcribing courtroom proceedings or legal depositions or things like that. So at Cobalt, we enjoy getting our fingers in many pies. By the way, remember I told you that ASR looks like this, right? That we improved that second orange layer, the DNN-based acoustic model. I should tell you, in all truthfulness, that the newest version of ASR doesn't look like that anymore. A lot of ASR that you'll find on the market still looks like that, or even possibly GMM-based. But the latest thing in speech, which has just really taken off in the last year or so, is this. Do you see the difference? We went from that to that. So that is, we had these separate models for all the acoustic features, the acoustic model, the lexicon, the language model, and now we have one model to rule them all, one big deep neural network to rule them all, right? So instead of 4 big matrices for acoustic modeling and then lots of other stuff, we now have something like, I don't know, 25 matrices, larger matrices, representing a much deeper model. This has led to real breakthroughs in even more robust, more accurate speech recognition. It's exciting, but it's still kind of frustrating at times because I can't tell you what's going on exactly in those matrices. If in the past our ASR misspelled a word, like let's say the French word chaise longue, which some Americans pronounce chaise lounge, inaccurately pronounced that way. If our ASR misspelled chaise longue, I would know what to do in the past. I would go into the lexicon, I would find where that entry was, and I would fix the spelling. But now I can't tell you in those matrices, I can't tell you where that spelling is stored. Where does it know that? So I don't have a way of fixing problems except by fixing the training data and training over again, or putting a Band-Aid, a patch on the output to say, if you ever see this misspelling, fix it, or things like that, right? And we do all of those things. But it's a little frustrating not knowing what's going on. Let me give you another example, but in something that's been in the news lately, in ChatGPT. ChatGPT is doing exactly the same thing as this. So is DALL-E 2 or a lot of other kinds of similar things. It's the same thing, just that instead of speech on the top, a big DNN, and text coming out the bottom, they have, maybe in the case of DALL-E, they have text on the top and a picture coming out at the bottom. Or in the case of ChatGPT, they have text going in the top and text coming out the bottom. It's all the same, right? By the way, we also at Cobalt are working on speech synthesizers, artificial voices, where we have text going in the top and speech coming out the bottom. So it's the same approach, using this the big what is often called an end-to-end DNN, or well, so as I said, this is the same kind of thing that's going on with ChatGPT. But here's an example. I typed this to ChatGPT just this afternoon, just to kind of, well, to see what it might know about some things. So I asked it, explain Asimov's 3 laws of robotics from the point of view of a politician running for the US Senate, who is also under investigation for misusing campaign finances. Okay, so it feeds it into that Chat GPT big DNN, and it comes out with that result. I'm not going to read that, you can read it. Chat GPT is doing the same thing, but it's trained on text, input text instead of input speech. And it also has its own collection of very large matrices and that activation function that represent that rules, the rules for ChatGPT. I can't tell you in those matrices, I can't point to where it knows Asimov's laws of robotics, or where it knows how someone running for Senate might speak, or how that speech might be affected by charges of financial impropriety. I don't know where it's doing that. I just know that it's working, right? This is part of what's exciting about it all, but it's also a little dangerous. I don't know, is that too strong a word? Since we don't really know what's going on. We live in an exciting time, and this new era of large, deep neural networks is still in its infancy. It's only a year or two old, maybe, in some cases less than that. It's exciting and a little concerning to think about where it's taking us. But I have to say, honestly, I'm much more excited than I am worried. I think we just need to stay on top of things, and we need to educate ourselves and others about the perils and the opportunities. All right. But this speech and AI are not spectator sports. They demand involvement from researchers, from entrepreneurs, from consumers and end users, and so on. And so I ask you to ask yourself, how are you going to get involved? I am an activist speech researcher, meaning that I'm constantly wanting to engage with people and figure out where the speech technology should be applied next. That future of speech technology is being written by all of us. And so I ask you to think, where might we apply this speech technology or other related technology? And I invite you to come talk to me. My email address is here, jeff@cobaltspeech.com, or you can always find me on LinkedIn and send me a message there. I apologize for my LinkedIn handle. It's maybe confusing, James Daff. That's an anagram of Jeff Adams. That way I can tell if someone sends me a message and says, "Hi, James," I know they don't really know me. They haven't even looked at my profile. So anyway, I look forward to hearing from some of you and engaging with you on opportunities that we can approach together. Thank you very much.